how many probabilities to specify this network?
9.
9. Okay, let me see. So there is 1 here, 2,
4.
4. Right? So you should be able to tell, by just looking at the network, how many probabilities. Okay. And then the next question was, I wanted P, A, not B, C, not D. Okay. This needs to be written as a product of numbers that are here. So remember that in this case, you have P of A. That's it. Okay. And here you have when A is true and A is false, what's the probability of B? Right? That's what you have here. So you have probability of B given A and probability of B given not A. Those are the two independent numbers you have there. Right? And similarly here you have probability of C given A, probability of C given not A. Those are the two independent numbers you have there. Okay? And then for this you have probability of B given BC, D given not B, C, B given not B, C, BD given B not C, BD given not B not C. Those are the probabilities you have. Right? Okay? And so, but I want this joint probability. Somehow I need to write this as, all joint probabilities themselves would be in terms of these existing probabilities here, right? And so you need to write it in terms of those probabilities. And for that, essentially, all we know, so tell me, what do I need to do? Start from P of A, because A doesn't depend upon anybody else. And then B depends on A, so it's not B given A. And C depends only on A, so C given A. And D depends on B and C, so P not D given not B and C. That's it. Now why am I allowed to do this? I'm allowed to do this because in essence what I decided to do, what I did was I wound up writing this whole thing, which is the order in which I wrote the chain rule. I had to write it the opposite way. Right? So basically I would have written the chain rule as P not D given A not B and C times P D, so not A, B, C, times, I can just actually do P, C, given A and not B, times P, A, P, not B given A, times P, A. Right? That's one chain rule instantiation. And when you did this, this not D given A, not B and C, not D given A, not B and C is just not D given not B and C. Because every node is conditionally independent of its non-descendants given its immediate parents. Okay, so A is a non-descendant, and I'm giving, if I give you the immediate parents, then A doesn't affect D. That's the point. So I will write this as, so this basically, this one will be this. Right? Okay? And similarly, C given A and not B, if you give A, C is independent of B, because it's independent of non-descendants given immediate parents. So that's why it's just because this is the same as this. 1, 1, 2, 2, and then not P given A is just not P given A, and A is A. Okay? So this, you don't actually need to remember this. I mean, this is essentially the theoretical justification as to why you could write this joint probability this way. When you actually look at any given single joint probability, you should be able to see that D only depends on B and C, B depends on A, C depends on A, and A doesn't depend on anybody. And so you know it should be P of A times P of B given A times P of C given A times P of D given B and C. You see what I'm saying? That's what I just wrote first. And these numbers are present. So for example, this is present here. This is present here. This is present here. This is present. Okay? So that's Bayes networks. Okay? So if you just want to use Bayes networks, you're done at this point. But you know, more apart from using Bayes networks, you also want to understand the semantics and understand efficient inference methods. So that's what we'll continue doing today. Any questions?